The following content is provided by MIT OpenCourseware under a Creative Commons license. Additional information about our license and MIT OpenCourseware in general is available at ocw.mit.edu.
We've been talking about the properties of transition metal complexes, coordination complexes, in the context of a simple crystal field theory model. And I just wanted to make reference at the beginning today to state diagrams. And in the context of octahedral complexes, you saw that an array of 6 ligands surrounding a central metal ion would lead to a T2G and what we're calling an EG star manifold of orbitals and on the metal, in which we can populate with the number of d electrons that we have present. And the graph that I'm making here is related to the idea that for a system with only a single electron, so this could be, for example, titanium OH2 6 times 3 plus. This is a D1 system, and it can go from a ground state configuration of T2G1 EG star 0, and then upon absorption of light, it can be promoted in from the ground state, represented here, into the excited state, and the excited state has the configuration T2G 0 EG star 1, showing that that electron has been promoted through absorption of a photon. And this gap here between T2G and EG star, of course, is our delta O value. And the axis on the bottom here is ligand field strength. Okay, so this is supposed to tell you that different ligands give rise to different values of delta O, accounting for the fact that this D1 titanium 3 ion in a field of water molecules has one color, whereas if you in fact look at TiCl6 3 minus, you'll be able to tell that that also is a titanium 3 plus or D1 system, but they do not have the same color. And the one absorption band that you find in the visible part of the spectrum that corresponds to promotion of an electron from T2G into EG star is just moving around a little bit in energy, because these ligands behave differently with respect to what we call their ligand field strength that they exert, that leads to a particular energy gap between T2G and EG star. Okay, so I'll get into this a little bit further in a moment, but the point is here that D1 or D9 are special electron counts. And the reason that they're special is that these have a single absorption peak due to what we call DD transitions. They have a single DD transition. And that means that there's a ground state and then just one excited state that the system can be promoted to in the presence of impinging photons of the right energy. And what happens is that if you have more d electrons than just one, or D9 is special because we treat that using a hole formalism, like there's just one electron missing from a complete manifold, a completely full D shell minus 1, with with DN systems, for example, D2 is much more complex. And this is beyond the scope of 511.2, but it's something that they're treating in 504, for example. So if you go on in inorganic chemistry, you'll learn how come different states can arise, multiple states arise when you have more than just a one electron picture. And in fact, so for example, if you have a vanadium 3+ ion, there are 3 bands observed. And so the simple picture that you have just a T2G level and an EG level is correct and maps onto the picture of the electronic states that are available, as long as we're just talking about a one electron picture. With more electrons in play, depending on just which of the orbitals they go into, they will have inter-electron repulsion terms that come into play and give rise to more excited states. Here, with 3 bands being observed in the visible, that means there's 3 possible transitions and 3 possible excited states that can be accessed. Okay, so it's a very complicated picture. And so we're going to be, for the purposes of this class, focusing on the one electron picture, but I just wanted you to be aware that it does get a lot more complex as soon as you go to many electron systems. Okay? Now let's talk just briefly about pairing energy. In the case of 3D systems, we typically find that the pairing energy is around 15 to 18,000 reciprocal centimeters is the typical energy unit given for pairing energy. But then if we go to heavier transition elements, to the 4D or the 5D elements, then typically the pairing energy is about 8 to 12,000 reciprocal centimeters. And what that says is that it's easier to pair up electrons in 4D or 5D orbitals than it is to put 2 electrons in the same 3D orbital. And the reason for that is just what the radial extension is of these orbitals. So if, in effect, these orbitals are larger than the 3D orbitals, and it means that if you put 2 electrons into the same 4D or 5D orbital, much of the time they can stay farther apart from each other than if they're in a 3D orbital. And so this has the practical consequence that 4D and 5D systems often are low spin. And so this high spin, low spin issue that we talked about last time is mostly focused on complexes of the 3D ions. So then we're talking about titanium, vanadium, chromium, etc. And if we come over here, we can ask, what is the effect of charge on delta O? So this is all pointing back to the state diagram that I showed you over there in this kind of sliding scale where you can change things like just what type of metal ion you have, 3D or 4D or 5D, or you can change the nature of the ligands, or you can even change the charge on the metal as a way of changing delta O. And so we can look at, for example, chromium hexaaquo 2+ versus chromium hexaaquo 3+. Okay, the first is a D4 ion, and then the second is a D3 ion. So you should practice going from a formula into the DN count, and then we can look at what delta O does. This is roughly 14,000 wave numbers. And then when we oxidize from 2+ to 3+, higher charge on the central metal delta O shoots up to about approximately 17,000, and this is in reciprocal centimeters. Okay, so we see that putting a higher charge on the metal center leads to a larger value of delta O. And that's also true if we look at some other metal systems along these lines. So for example, there are just a number of different metals for which the hexa-aquo systems can be generated in both the 2+ and the 3+ state of charge. And here we go from about 12,000 and then oxidize, and we get up to about 18,000. Okay, so even a larger increase in the value of delta O on going from the 2+ to the 3+ oxidation state of the metal. And then in the notes you'll find that I put in another example that behaves similarly based on cobalt. So if you go from cobalt 2 to cobalt 3 hexa-aquo, you go from about 9,000 up to 18,000 reciprocal centimeters. So almost doubling the value of delta O by removing one electron from the system. Okay, what's going on here is that the greater charge pulls the ligands in closer to the metal. And if the ligands are in closer to the metal, then what that ends up saying, as you'll see in a moment, because we're going to get to the MO picture for octahedral coordination complexes, is that putting electrons in EG star becomes more difficult. Delta O is larger. The ligands come in closer, and that is effectively shrinking that value of R when we talked about our spherical coordinates as applied to the angular parts of the d orbital wave functions and looking at that. So we're changing R. The ligands are coming in closer to the more positively charged metal ion in that case. And then we can also look at the effect of changing the ligand. So in the system on the left, we were looking at pairs of metal complexes with the same ligand and changing the charge, and now we're just going to say what happens if you change the ligand. And this will be a series of vanadium complexes. We've got 5 of them. We've got the vanadium hexa-aquo, and these are all going to be, well, this one's 3+. We've got the vanadium with 6 urea molecules, and this is also 3+. We've got vanadium hexafluoride 3-, and these are all vanadium in the +3 oxidation state. Then we have vanadium hexachloride 3-, and down here the 5th one will be vanadium with 6 cyanide ligands and 3-. So these are all D2 systems with vanadium in the +3 oxidation state. And here we're going from 18,000 reciprocal centimeters to the hexafluoride. We drop down to 16,000, and then this is all approximate, and 6 ureas on vanadium. We go up to about 17,000, and then with the hexachloride we're down to about a delta O of 12,000 reciprocal centimeters, and then you put cyanides on, and delta O pops up to about 23,000 wave numbers. So this is the same metal ion, but in 5 different ligand environments, it has 5 very different values of delta O. Okay? And from this, we can derive a spectrochemical series. For organizing ligands with respect to the magnitude of delta O that they exert for a given metal ion. And this one just gives us a series that contains 5 ligands, but as you can imagine, many more ligands than just these 5 simple ligands have been looked at with a variety of different metal ions to make a pretty big overall comprehensive spectrochemical series that sort of allows you to pick out which ligand you want when you're interested in generate a particular value of delta O. And here what you see is that the weakest one is chloride. We have chloride, and then next was fluoride, and then next was urea, followed by water, and then the strongest in this small series of 5 was cyanide. Okay, and when we try to understand the order that these different ligands appear in the spectrochemical series, we're going to find out, as we study the properties of the molecular orbitals of these systems, that cyanide is a pi acid, and that down here, chloride is a pi donor. And in the middle, you have systems like water, which is more or less sigma only. Okay, so we can understand where specific ligands appear in the spectrochemical series on the basis of their orbital considerations. And that will be the focus of the next part of the lecture. Okay, I'd like to talk a little bit about sigma-only ligands. The process in which we are now about to engage is very similar to that we used in class for generating the molecular orbital energy level diagram for the BH3 molecule. Okay, in that case, we had a central boron and 3 hydrogens around it, and we made some hydrogen linear combinations, and then we saw how they would interact with the atomic orbitals of the boron. And now we're going to do the same thing, except we have a lot more orbitals in the system as a whole, so we're approximating some of them. Here's a typical sigma-only ligand, NH3. And for NH3, we've got a lone pair on the nitrogen here, and I'm drawing it in very simplified fashion, as you'll no doubt appreciate. There's our lone pair, and when this points directly at the metal, the lone pair can make a sigma bond to the metal. Okay, I think you'll appreciate that if we have a metal out here, such that this lone pair of electrons is directed right at the metal, then that results in a cylindrically symmetric lone pair about that metal-nitrogen internuclear axis, and so that would be a sigma type of interaction. So this is called a sigma-only ligand, and other ligands, like cyanide or like chloride, we're going to have to add in pi effects. But this is the simple sigma-only case. And so if you take a molecule such as this cobalt hexamine (2+), then, or actually, let's say 3+ for simplicity here, cobalt 3+, and we have these NH3 ligands at each of the 6 positions. And in each case, the orientation of the hydrogens on these nitrogens is such as to promote a sigma directing effect of that lone pair toward the metal. And so that lone pair of electrons on the nitrogen for each of these ammonia ligands, directed right at the metal, is providing this repulsion that pumps Eg up in energy. Okay? And you'll see that hopefully very clearly now. And let me point out that this orbital here that I'm focusing on is the HOMO of NH3. Okay, so what we're doing is we're saying you have a central metal ion, and then you have 6 ammonia ligands pointing at it, each of them pointing their HOMO at the metal, their highest occupied molecular orbital. What does that do? What kind of bonds arise as a consequence of that between the metal ion and these 6 ammonia molecules? And so we'll now see what that is on the basis of some of the linear combinations that we can generate between the 6 HOMOs of the NH3s in this kind of a geometry. I'll do the first one over here. Okay, I'd like to use a different color for that. Let me use my blue. All right, so I'm going to draw for you some linear combinations of ammonia lone pairs. These are simplistically representing the HOMO of each NH3 directed at the metal. That one has the symmetry of a cobalt s orbital. It has the same sign everywhere. Okay? And then we're going to see that you can draw 3 of these. And I'll draw them all right here. In pairs. And this one has the symmetry of a cobalt PZ atomic orbital. You see it's got positive up here and down here. We're taking this to be X, this to be Y, and this to be Z for each of our diagrams, so that the phase properties of this combination is that of PZ. This one is like PX. This one is like PY. And the only reason we have to take these linear combinations is because we have multiple equivalent ammonia molecules in this problem. And then we have 2 more that will be of interest to us. One of these will have a couple of big lobes located on Z, pointed at the metal, and then 4 small lobes, each with negative phase. So I'll shade them to indicate that negative phase. And that one will have the same phase properties as a cobalt DZ squared orbital. Plus above, plus below, and then to match up with the torus in the center of DZ squared in the XY plane, the negative phase shown there. And then finally over here, we have one where all 4 contributions to this one are in the XY plane along the X and Y axes, and with shading as shown there. And that is of the same symmetry as our dx squared minus y squared orbital. Okay, so having written down this set of 6 linear combinations that we can generate from our 6 ammonia HOMOs, we're done, because the cobalt has atomic orbitals of these symmetries. We can now use these to make bonds between the ammonia molecules and the cobalt, and we can use them to make corresponding antibonds. So here's the MO diagram for the sigma-only case. what we have is an energy level diagram that will represent the interaction of these linear combinations with the metal valence orbitals. And so I'm going to draw the metal valence orbitals over here as follows. We have on the metal the 3d, the 4s, and the 4p. And some of you will notice that this ordering of energies is a little different than what you saw when you just built up atomic configurations. Because what I've drawn here is that the set of 5d orbitals, the set of 5 3d atomic orbitals, is down lower in energy than the cobalt 4s, and lower in energy, that is, even still, than the cobalt 4p. This is our cobalt atom here. And the reason this energy ordering for the valence orbitals is different is because we have an ionized cobalt. And the energies change around when you remove an electron from the system as compared to the neutral atom. But one thing that will help you remember this ordering of energy levels is that it goes in the order of the principal quantum number, which kind of does make a little sense. In fact, these energies switch around depending on which of the metals you're talking about. But generally 3d and 4s, or alternatively 4d and 5s, are pretty close in energy to each other, depending on the ion that you're talking about. And then 4p is usually energetically a bit separated from that. And then the thing that makes us focus our attention so strongly on the d orbitals is that those are the ones closest in energy to the ligand orbitals that can interact with them. And so let me draw over here a bar that represents the 6 LCs of NH3 homos. So in essence, this represents these 6 drawings that I drew over here. Linear combinations that have the right symmetry to interact with certain of the valence orbitals on the cobalt here on the left. And what we'll find is that we'll start with the 3D, since that's what we're going to be principally interested in here. We come over and we find that 3 of the d orbitals do not match any of these because these NH3 homos all lie in nodal surfaces of them. And that will be, of course, our T2G set. So those have the same energy as in the ion itself. They come straight over, and they don't get involved in bonding or anti-bonding interactions. These are non-bonding. Okay, that's T2G. And then what we find is that of these 6 linear combinations, 2 of them, shown right here, have the correct phase properties to make bonding and anti-bonding combinations by interacting with dz squared and dx squared minus y squared. So we show that down here. Here's a bonding combination. This has EG symmetry, and it represents the formation of 2 bonds between the metal and the ligands. And of course, we also make an anti-bonding combination of the same symmetry. So this should just remind you of the hydrogen H2 molecule molecular orbital problem built into this much larger structure. And this one, this anti-bonding case, is EG star. Okay? And let's just quickly look at them. Here what we have is a DZ squared orbital with its torus interacting in an out-of-phase manner with these ammonia lone pairs. That creates antibonding character here and here, making this a high-energy orbital. And then we have antibonding character 2 in between each of the ammonias located on the XY plane and the torus of the DZ squared. So that is one of our two EG star orbitals. And over here, we have our dx squared minus y squared orbital, making antibonding interactions with this other linear combination, as shown here, such that we get antibonding all the way around. Okay, that's EG star. That is the reason why the EG set derived from our set of d orbitals is marked with an asterisk. It's antibonding with respect to these bonds. So if you start to populate EG star with electrons, as you will do in certain cases that are high spin, for example, those electrons that go into EG star, if you reflect back on the way that we calculate bond order, they go in there and they weaken these two metal ligand bonds. And these two bonds look just identical to the ones I drew here for EG star, just reversing the phase and making them bonding everywhere. So let's just look at those. Here we have DZ squared, making a nice bonding combination. So it's interacting in an in-phase manner with that linear combination. So we have bonding both in the XY plane and strongly along the z-axis. That's a bond. That's one of these two bonds. And then over here we'll have x squared minus y squared, making bonds also like that. Okay, so these are down here. This is bonding, and this is antibonding. Okay, now that's not the entire diagram. One runs out of space pretty quickly on these horizontally oriented boards for putting together tall MO diagrams. But there were 6 LCs over here, and you'll see that there will be another one that makes a bond with the 4s orbital. And so accordingly, the 4s orbital comes up here. There will be an antibond derived from 4s. There will be also a set of 3 that are antibonding derived from interaction of 4p with the other ones here. And there's a big energy mismatch between 4p and these, so we'll draw these as the least stabilized of the set. But now what you can see down here is that we've found a way to form 6 bonds, 6 pairs of electrons, each coming from the highest occupied molecular orbital of the 6 ammonia molecules. We've formed 6 bonds using these valence orbitals of the metal. And how many more electrons do we have to put into the diagram? We have 6, because this, in the case of our cobalt NH3 6 3 plus, this is group 9, minus 3 for the 3 plus charge. All the ammonia ligands are neutral, equals 6. So this is a D6 case. So the orbitals here that we call T2, G, and EG star can now take up 6 more electrons. And I'm drawing them in here with the assumption that this is a low spin case. And that's reasonable based on the 3+ charge of this ion. We have already discussed the effective charge. It draws the ligands in. It tends to increase the value of delta O, as we've seen. And so this is how I would populate that diagram, with the 6 d electrons going into the non-bonding T2G, constituting the highest occupied molecular orbital of this system, and then stabilize the lone pairs. Down here, what's really going on, you can think about these 6 ammonia molecules acting simultaneously as 6 Lewis bases to a metal that has enough empty orbitals to accept 6 lone pair donations to that same metal. So it's a Lewis acid times 6. And it's positively charged, which of course tends to draw electron density to it. And that is our simplified molecular orbital diagram for the sigma-only case. Now there are a lot of other interesting cases, as you can see here from this spectrochemical series, where the ligands in the middle are basically sigma-only, urea, water. But then at either end of the spectrochemical series, you get into systems where you must take pi effects into account. And we'll treat first the case of a pi donor. Remember that if we're talking about a donor, that means we're effectively talking about a Lewis base. And you have to ask yourself the question, in a system that has a ligand that can make pi bonds, are the orbitals on the metal that have pi symmetry filled, or are they empty? And similarly, are the pi symmetry orbitals on the ligand in question filled, or are they empty? And if you can get all that right, you'll really understand what happens in terms of attenuating T2G when you add in pi effects. We've seen that the EG orbitals of a metal are the dz squared and dx squared minus y squared that point along the axes. The ones xz, yz, and xy that point between the axes have the potential to make pi bonds with ligands. And so here's an example of a type of ligand that can make pi bonds to a metal. This ligand is NH2 minus, and it can make both sigma and pi bonds to a metal. It's usually the case that if a ligand is capable of making pi bonds to a metal, it's also capable of making sigma bonds. And so the pi effects are sort of mapped onto the sigma framework. And so what we've found over here and here about the sigma-only case, that'll also be true for pi systems, but then we're superposing on that diagram the pi bonds that can form in the system. And the way that NH2 minus can make both sigma and pi bonds with a metal is, first of all, it has a lone pair that's directed at the metal, like this. For forming sigma contacts. And if you have 6 of these around a metal, the situation would be just the same as what we derived over here for the cobalt hexamine. But this is a planar system. The sum of the bond angles around the nitrogen in systems like this are 360 degrees, meaning that unlike ammonia itself, which is a trigonal pyramid, this is a planar system, and so it has a lone pair perpendicular to that plane. I'll draw it that way. It's just a pure p orbital perpendicular to the plane of the substituents on that nitrogen. And the way that that could make a pi bond with the metal is through simultaneous donation above and below the plane of substituents on that nitrogen. So that this ligand can interact as a double Lewis base with a metal if the metal has appropriate orbitals available. Okay, so a situation in which you might find this would be the following. An example of such a molecule, this would be a neutral one. And what you see is that the planes of these NH2 units are aligning up with the x, with the coordinate xz, yz, and xy planes, Cartesian planes in the molecule. This one, since each of these ligands is negatively charged, and the chromium, the molecule is neutral, the chromium is therefore in the +6 oxidation state to balance the 6 negative charges on the ammonia, on the amido ligands we call them. This is amido. And so this one, in fact, is a D0 case. Okay, and D0 is an electron count that is pretty typical for the formation of pi bonds from ligands that can donate into the metal center. If you have d electrons present in a system like this, then you won't have the empty d orbitals on the metal that are necessary to accept bonds formed by lone pair donation of this sort. The system will become choked up on itself with too many electrons. So let's see what those perturbations will lead to for our MO diagram. I'm going to focus in on linear combinations of amide lone pair orbitals that in fact have the correct symmetry to interact with our T2G set, since that's our pi set of orbitals from the D manifold on the metal. So let's look at this. This would be DYZ. And then let me choose like this. We can make a pi bond of this sort using a linear combination that I'm mating up together with the DYZ orbital. And while I've drawn here the bonding counterpart, there, of course, will be an anti-bonding counterpart to that. And then let's draw the one that belongs to DXZ. And that will be the one up top here. Making so what we've got are pi bonding happening here, 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 and here that corresponds to pi lone pair donation into that metal orbital. And then finally we have one that involves the DXY. And this would be with our hydrogens up and down, here and here. Sorry, no, this is out here. Up and down in front and in back, like that, so that we can make 2 pi bonding interactions over here like this. Okay, so there's pi bonding, bonding, bonding. So at this point, we've gotten to where we can recognize how there are 3 linear combinations of the pi lone pairs from these amido ligands that will have the correct symmetry to interact with the T2G set from our metal. There are 3 more where you would just flip one of the 2 on each, and those would have the correct symmetry to interact with the px, py, and pz orbitals on the metal. Okay, I'm not going to draw those out since we're focusing on the D part of our diagram at the moment. And what we'll find then is in the molecular orbital diagram for a system of this sort is that our D manifold, this is our 3D, 4S, 4P, is such that you remember previously T2G came straight over, and now instead we're going to see that it goes up in energy because what T2G now is, it still has a lot of dxz, dyz, and dxy, but now T2G has acquired pi star character due to the fact that we have these linear combinations over here. These are our pi LCs that we drew over there that are of the appropriate symmetry to interact with dxz, dyz, and dxy, and therefore these, which are filled, are stabilized, come down here, and form a T2G set that is bonding, because those, of course, are filled in NH2 minus. And if the metal has an empty T2G set, you see that we do get 3 pi bonds. T2G now gives us pi antibonds. This is being mapped on the sigma framework that is the same as what we have right here for the cobalt hexamine, so that above T2G we will have the EG star, and you'll now recognize that EG is sigma star rather than pi star, so it is more strongly destabilized due to the greater overlap considerations of forming sigma bonds versus the side-to-side overlap of pi bonds. And the key observation here is that pi donors decrease the magnitude of delta O by raising the energy of T2G, by making T2G pi star in character, antibonding. Okay? So we can see not only that T2G should be raised up, but that mapping that onto our full sigma framework diagram, delta O is shrinking. We still have our 6 sigma bonds between the NH2 ligands and the metal. They're down here, just not drawn. It's the same as up here. And now we have 3 additional pi bonds. There's another 3 additional pi bonds that you can draw that is because we do have 6 of these NH2 minus ligands, and then the corresponding anti-bonding orbitals involve 4p, and they're way up here somewhere in energy and very empty. Since this was a D0 case, what we have is that you've got 12 pairs of electrons on 6 NH2 minuses that are down here in this manifold of metal ligand sigma and pi bonding. And so we've got 12 pairs of electrons down here that describe the sigma plus pi bonding between the metal and the ligands. And then you come up here to your D manifold. These are empty because this is a D0 case. Because I happen to choose chromium in the 6+ oxidation state here. So it's a D0 case, and we wouldn't have any electrons to put in here, but under these circumstances, in order to get color in a system like this, you would have to be promoting an electron from down here, from these pi bonds probably, into the D manifold, for example. And what we've seen here, namely that pi donors decrease delta O, should give you a clue as to what's going on with chloride and fluoride. Since those have small values of delta O, they lie at a position of weakness in the spectrochemical series. And then the converse, that ligands like cyanide and especially carbon monoxide are very high in the spectrochemical series because they are pi acid ligands. And this is something you'll be getting more information about in recitation this week. So see you all on Wednesday.